Recording.
All right, I think we should get started. Thank you everyone for joining us. It is my pleasure to introduce Paul Tiede. I just learned how to pronounce his last name right. So Paul is currently a Black Hole Explorer Fellow, that's called BEX, and he used to be an Event Horizon Telescope Fellow, and he's been working in all kind of black hole observation stuff, I imagine. So excited to hear about it. The floor is yours, Tina. Oh.
I got it. I think I have a mic here. Hopefully it's on. I have a loud voice. Okay, so yeah, thanks. I'm gonna talk a little bit about unlocking black hole physics with computational astronomy. This is kind of something I've been working on since I've been here at the CFA and a little bit during my PhD at the University of Waterloo. But so if you want to learn something about black holes, you have to pick an instrument. My instrument of choice, as you can imagine, is the Event Horizon Telescope. It is a global collaboration. That's one of the best parts about it, is you get to kind of effectively travel all over the world. I went to Greenland last year to assist in an observation. That was pretty fun. But we have currently 11 telescopes at 9 distinct geographic locations that spread around Hawaii, mainland US, Mexico, Chile, France, Spain, and Greenland, and then of course the South Pole. South Pole is kind of fun for a few reasons. But thanks to the Event Horizon Telescope and this global array, we were effectively able to turn the entire Earth into a dish or a telescope. And because of the ability to turn the entire Earth into a telescope, in April 2019, we took the first ever image of a black hole on horizon scales. I think this is the image that a lot of people are familiar with. It blew up. How I knew we were exploding on the scene was when the memes started to appear on Twitter. That's how you know you've made it in science, is when they start memeing your image. So this was the original image, and about 2 years later, we released a polarized version of the image. This isn't higher resolution. It's effectively the exact same resolution, but these thin lines here denote effectively the polarization of light, or they kind of trace the magnetic field that is around the black hole M87. About a year after that, we produced the first image of the black hole Sagittarius A star. This is the black hole at the center of our galaxy. And I think one of the things that was the most striking to me when we produced these images was actually how similar they look. So these M87 and Sag J star are actually quite different black holes. M87 is about 6 billion times the mass of our sun. And on scales, that's about the size of our solar system. So it's big. Sagittarius A star is only, and I say only, but it's about 4 million times the mass of our sun, and about out to Mercury or a little beyond Mercury. So these are incredibly different black holes in terms of scale. However, both these images share a lot of similarities. They're both a bright, puffy ring with a central depression. Maybe some of the details of where they're bright differ, but a lot of these features are similar. And it actually turns out that this is a prediction of general relativity, that for these types of accretion flows, we expect all images to look like this. And the reason is that around this black hole is effectively an accretion disk, and the majority of the emission we see is light that comes from this accretion disk to our eye. However, there's also additional emission, and what this comes from is the fact that light can take many half orbits around the black hole just due to how strong gravity is. And as a result of these half orbits, you end up with effectively demagnifying this entire accretion disk into this very thin annulus that we would call a photon ring. And so what we think we're looking at is what we think we would be seeing if we had an infinite resolution telescope is something that looks like this, where you have this puffy emission. So this is the accretion disk, or light that comes straight to you. It's called colloquially the n=0 photon ring. And then on top of that, you would expect to see nested sets of very thin, bright rings. And then in the center, you see this so-called, what we call the inner shadow. And what this is actually the footprint of the horizon. So a horizon doesn't emit light. It's effectively an infinite redshift surface. And so you expect to see some sort of very dark central region. And now, of course, we don't observe that because we have a finite resolution telescope. So we expect to see some blurry version of this image. However, one of the really interesting things about working on the EHT is that it is a computational telescope from beginning to end. I'd say we actually even form the telescope through computation. And by that I mean is we have this global array of telescopes, but all they do is they know at this time, we're all going to point at this part of the sky. Each of these telescopes then measures an incoming electric field or a voltage. It then immediately digitizes it. So if you know some signal processing, we use something called 2-bit quantization. It's 1 above 1 bit. So we don't just record if the electric signal is on or off. We also measure off, kind of on, really on. And that's all the information we have from each telescope. Even with that, the EHT records something about 1 to 10 petabytes of raw data. These data is then immediately recorded onto hard disks and shipped to a central location. And once it's shipped to a central location, this is actually where we form the telescope. So we form the telescope through specialized supercomputers called correlators. These correlators take these 2-bit quantized signals, cross-correlate them, and this is where we actually effectively form the Event Horizon Telescope, or form this effectively Earth-sized aperture. Once we do that, we go from about 10 petabytes to 100 terabytes, maybe 10 terabytes. However, this is not the end. What comes out of the correlator is effectively noise. It's very weak signal data, and this is for a few reasons. The big one is that the atmosphere is above us, and the atmosphere scrambles our signal on the time scales of seconds. And so because of this, we can't just take this raw output, and instead you have to rely on a process called fringe fitting or calibration, where we effectively look for the signal that's like SNR much less than 1, find this signal, remove this atmospheric effect, and then average a ton, and an absolute monster amount, because we go from 10 to 100 terabytes to about 10 to 100 megabytes. This is a massive amount of data reduction. Once you get that though, this is really the data that I work with directly these days, or that most of the members of EHT work with when we're taking an image of a black hole. The very, very last step of the process is image reconstruction, where we go from this data and we try to figure out what the source on the sky is. And part of the thing that makes this really hard is that the EHT doesn't actually take an image of a black hole. It is an interferometer. What we actually measure are samples in the Fourier domain. So each pair of telescopes measures a single Fourier component, really 2 because the image is real, so we can do some symmetry arguments, but effectively a single Fourier component. And if you just had something like 10 dishes, you'd have something like 25 kind of samples, and that's not a lot. So what we rely on actually is that the Earth rotates in a process called aperture synthesis. And because the Earth rotates, we're able to trace out tracks in the UV domain, or in this Fourier domain, and this is what really fills in our telescope and gives us enough information to form an image. However, forming an image is still really hard. You imagine again, we had a perfect resolution telescope and our on-sky image looked like this. Now, if I had infinite money, or if I was Elon Musk, I would build a radio telescope on every square meter on the planet, fill in the entire aperture, not have to worry about any kind of instrumental effects, and effectively just be able to take an inverse Fourier transform of the data, producing a perfect image. Unfortunately, I can't do that. And our actual coverage looks like this. And so what this means is that there's effectively no single image that will fit the data. And instead, we'll have infinitely many images. And one of the big things with us is that uncertainty is uncertainty in what the image looks like is very, very high. Maybe it's a ring, maybe it's a disk, maybe it's a double. We're not sure. And you kind of want some way to classify this. Unfortunately, traditional VLBI data processing ignores this uncertainty. And there's a lot of reasons for this. A big one is that this was really pioneered in the 70s and 80s, and computers were small. And so you really just wanted to be able to get an image out, and there wasn't really the computational power, I think, to really suss things out. And so how some of these traditional methods work is you start with a guess, something like maybe a point source or a Gaussian or something else. You see if that looks like the data. Then maybe you do some residual calibration to take out some of residual atmospheric effects. And then you're like, this doesn't do good. This isn't doing a great job. Let's add a second point. Oh, Maybe we'll run some more calibration. It still doesn't look good. Maybe add some more, maybe add some more, maybe add some more. And then until you kind of are like, yeah, this is probably good, and you stop. If this sounds heuristic, it's because it is. Traditional VLBI astronomy is literally dominated by heuristics, and the people who would do this kind of work were called artists. And there are people on the planet who are just better at this than other people because they have intuition, they have experience, they have a whole bunch of nebulous things that I would have a hard time teaching to a student. It's kind of feel. And the other thing about this is each one of these methods, or if you get the best artist in the world, they will still produce a single image. So for instance, this is an example of an image that you might get from some sort of VLBI program. This is from Mojave. And what a traditional VLBI astronomer would be like, oh, look, this core region, this is bright. We probably believe this. There's some fluffy stuff up here. Maybe there's some emission here, but I might not know the details. And so typically the traditional thing is to gain confidence, you observe it a ton. And so you'll look at the same source over multiple epochs with multiple frequencies, and you'll build some confidence about what is real. So from this is the same source observed a whole bunch of different times. You can see this core region looks very similar in each image. So you might be like, okay, this core region is very certain. We know it's there. This extended emission changes a lot. Now, this change could be due to maybe the artist picked different choices, or maybe the UV coverage or the Fourier coverage looked a little different, or maybe the source evolved. And this does happen. These sources do evolve. And so what you might go is, okay, this core region, we know there's probably some secondary emission up here, but you might not believe a lot of the details. And as a result of this, I would say traditional radio astronomy is filled with doubt. There's literally been decades of fighting over things that are real or not real. So for instance, this is a picture of M87. This is the black hole that we took a picture of. However, this is at a lower frequency, so you're seeing a lot larger extended features. Our image is effectively this little core right here. But this is a very well-known image. This was a lot of work to produce this image. A seasoned VLBI astronomer would be like, artifact, all this kind of stuff is just artifacts due to our image reconstruction algorithm. Don't believe it. However, someone may come along and ask, what about this extension down here? Is this real? Do we believe it? And some people might say, yes, that's real. Other people will be like, no, that can't be real. And you will literally have decades of fighting about whether this extension is real, whether it exists, or whether you can trust the brightness. Then someone else might come along and say, what about the, and hit the wrong button. Come along and be like, well, what about these extensions up here? And as there has literally been decades of fighting over this. And I think we're coming to a regime where we believe some of this extension stuff, but it's been a long time. And so one of the things that EHT really pioneered was, instead of looking at a single image, they developed what I'm going to call survey imaging. This is not colloquially what it's called in the field. I came up with this just now, because I needed some name for it. But effectively is, we have all of these choices that these artists will make. What we want to do is codify it. And what we codify it is into effectively, we search over all of these things using effectively a grid search. One of the predominant methods that the EHT has used is something called regularized maximum likelihood. This is similar to chi-squared fitting that I think a lot of people are familiar with in astronomy, where you have some cost function, effectively, this J here. You have some data terms, these are your data chi-squareds, and then you have regularizers. And these regularizers enforce things like image smoothness, maybe sparsity in the image or similarity to something. But with each one of these regularizers comes a hyperparameter, and these hyperparameters kind of code how much you want to enforce it. If you increase the regularization, you increase lambda, so we might force more smoothness. However, you have to, what hyperparameters you pick or what hyperparameters perform on your data, optimally, it really depends on what the intrinsic structure is. You can imagine that if you have a very smooth, effectively flat emission region, you might want a different set of hyperparameters that there's a set of point sources. And so you need some way to figure out which hyperparameters perform best. And so what the EHT did, and this is at least part of the connection to machine learning, was we kind of took an approach that's very similar to the machine learning test predict and move and then apply to held out data. And so what we did is we created a synthetic set of data or a training set based off of image structures we thought what the black hole could potentially look like. These include things like rings with no brightness asymmetry, crescents, disks, doubles. You make a whole bunch of synthetic data, and then you do this effective grid search over your set of hyperparameters. And this is what at least part of the output looks like for this crescent one. And so what you can see here is that for a lot of the image reconstructions, it looks like a ring. And then there's some things down here that kind of just looks like a blobby kind of waffly thing. And so once you have this set, you have to select the best image. The way this was done was with heuristics. So to select the best image, we did it based off similarity with some truth. How similar and what value we say is similar enough is effectively a decision that we made. And then on top of that, how well we actually fit the data. And then, you can add others as well. Once you do this, you get you effectively remove a large amount of this grid search, and you're left with a much smaller set of images or your top performing set of hyperparameters, and we're intelligent and creative, so we call it the top set. Once you get this top set, you can then just apply the set of image hyperparameters that we think are good to the real data and producing images of M87. And this is what we actually produced in the original EHT results. We show a single image, but in reality, we actually have thousands of images that we think describe the data well. And in all of the images for M87, we see this kind of ring-like structure. And so, at least from the collaboration, we have a lot of confidence that this is effectively the general structure of the M87 images. And you can find a lot of this in and reproduce this in the excellent EHT imaging library. It's a Python library that was developed here by many people, including Andrew Shale as the lead. However, there are some limitations of this survey-based imaging. I'm a bit of a computational person. So the first thing for me is these lambdas, this grid search will just scale poorly. As we increase the number of points we want to look in this grid, it's going to scale bad. If we increase the number of hyperparameters, it's going to scale geometrically. And for our 2019 imaging results, with our very sparse EHT data, the imaging results already required about a week with some amount of high performance computing. However, there's another point, and this is that very similar to machine learning, where if you pick your training data, if your training data is not great, like let's say you're trying to reproduce an image of a flower and my training set's a bunch of cats, you might not do a great job of producing your flower image. And this is the same thing that we had with EHT. And what this is that selecting our synthetic data requires us, or building our training set requires us to kind of know what the image looks like. The EHT is in a really interesting regime where we have no idea what we're going to what it's going to look like. These are the highest resolution images ever produced. And so we've never really seen black holes on this scale before. So we wanted to a priori assume very little. And as a result, the training set we actually used in 2019 was not optimal for certain image features. I demonstrated that a paper in 2022 that we were actually entirely insensitive to ellipticity in the ring as if it existed in some certain direction. So if the actual black hole was elliptical in this east-west direction, our imaging top sets would have always reproduced these circular type rings. And so these top set images could actually induce bias into our results. And you might be like, who cares if it's circular instead of elliptical? This actually matters quite a bit. General relativity predicts that this should be a pretty circular ring. And so if it was highly elliptical, it would mean something about the emission region and the emission geometry around the black hole. So these types of biases can have actually a direct impact on the type of science that we ultimately want to do. So to kind of overcome this, during my PhD in the last few years, I've been trying to pioneer the field of Bayesian imaging in VLBI astronomy. This is actually very new. Bayesian imaging really didn't exist as a concept, or really wasn't really explored in this type of domain until very recently. The benefit of Bayesian imaging is that I can codify exactly what assumptions I am making in a very straightforward way. So I can start with my image model. I might be some sort of power spectrum type thing. So I'll assume the image has some effective power spectrum, some effective correlation length, some amount of variability. And then on top of that, I can actually directly include in my model residual calibration errors. This is actually important. One of the dominant sources of uncertainty in our images are calibration artifacts. So having some way to simultaneously solve for the image and the instrument model is actually quite important. Once you do that, you can put it together and produce an observation. And then we could do the standard Bayesian thing, find the posterior and pick your posterior explorer of choice, whether it's an MCMC method like Hamiltonian Monte Carlo, a variational method, a Laplace approximation, or something similar. But as a result, starting in 2020, led by my former supervisor Avery Broderick, Dom Pesce here, who's at the CFA as well, and myself, and a series of papers presented some of the first Bayesian images of M87. And as a result of this, we were able to assess things like what's the mean image or the average structure, and what aspects of the image are certain and uncertain. However, to get performance, we required us to write this in C++. And even with this, it took about a week to get this image with about 1,000 CPU cores. I basically heated the planet a little bit myself there, producing this. Not great.
Well, can I ask you?
Yeah.
I'll get that. Is the forward model there differentiable?
Yeah.
Yeah, it is. Okay.
We'll get to that. Yeah, it is differentiable. So I'll get to that in a little bit. Okay, so performance is a problem with the EHT. So the survey imaging took about a week with 100 cores. This Bayesian imaging, which I'm going to be upfront and say was a bit of a toy problem. We restricted ourselves to a very small number of pixels, so about 25 pixels in the image, just because we were really worried about scaling. And this is a problem because the EHT has a data problem. And by a data problem, I mean, we have only published data from 2 years of observation, 2017, and just started doing 2018. However, we have recorded and available data in 2017, 2018, 2021, 2022, 2023, 2024. And we're probably going to observe in 2025. We're probably going to observe in 2026. And so we are facing a problem where we just have a lot of data that we haven't explained. And this type of performance is effectively going to start to become unacceptable. And so one of the things I have developed in the last couple of years is a new package called COMRAD, or Composable Modeling of Radio Emission. The acronym's a mouthful. And what we did is we chose to use the Julia programming language for this. There's a few reasons. A big one is Julia tends to blend performance and ease of use in a way that maybe Python or C++ don't. It also has pretty rich support for GPUs. I think it has some of the best support for GPUs in the sense that any GPU you can imagine we can run at least partially on. So there's things like CUDA, AMD, Intel, and even Metal. Metal support's a little spotty. That's not Julia's fault. That's the Metal language itself's fault, but it wasn't really built for scientific computing. It also has a pretty rich ecosystem and interactive development. And so the real reason for why Julia, why do I dare pick a different language than Python, which is the standard in astronomy, or C++, which is also a pretty well-defined language at this point in astronomy, and well, one of the most popular languages, period. Well, Python is slow. I will also argue Python is not as nice as you would imagine, especially for package management. Pip's dependency resolver is horribly slow. Conda itself is slow and buggy. You also have Mamba, you also have UV, you also have, I swear, every 2 weeks, a new package manager in Python. And the amount of times we've had environments blow up on us because of Python's dependency handler is not small. As well, from a performance standpoint, to get good performance in Python, you rely on vectorization, whether it's calling into a NumPy library or a JAX library. These work extremely well. They are feats of engineering, and I applaud those people excessively. However, vectorization is just sometimes not super useful to write your models in, especially if you're wanting to be very flexible. From a C++ standpoint, there is no package management. You're having to compile your makefiles yourself. Unless you're using some outside tool, maybe like Nix. But There is very little package management. There's also low-level programming. Someone who's coded in C++ a lot. The number of times I've had a seg fault or some memory issue is quite large. Julia is nice in the sense that it has a Rust-like package manager, so it's very easy to add external dependencies. It's also garbage collected. Benefits, downsides to this, but at least from a scientific software point, being garbage collected is nice. I don't have to worry about memory management. It's also typically within a factor of 2 of speed of the C, so we can, with some effort, get near C type performance. And then it has GPU support, yada, yada, yada. And so with all that being said, what kind of performance do you get with Comrade? Well, as a recall, we're talking about weak with high performance type things. With Julia and Enzyme, which I'll talk about briefly, we're down about 30 minutes on a single core on your laptop. And as well, we were able to effectively scale these Bayesian methods from about 25 parameters to 1,000 parameters. So this moves black hole imaging, publication quality black hole imaging, from something I would need to run on Harvard's cluster to something you can sit down in an afternoon and produce on your laptop. So this is a pretty big performance boost for us. It's in fact about over a greater than 3 order of magnitude improvement in time and computational resources with respect to the standard tools. And at least part of the reason for this is, or a big part of the reason for this is computational improvements. And specifically, we're utilizing something called Enzyme. Enzyme was developed at MIT in the CSAIL department by a guy named Billy Moses. He was a PhD student, now he's a faculty member at UIUC, and as well Valentin Shiravi, a MIT CSAIL and Julia Lab member. Enzyme is a little bit different than your standard AD tool. If you're familiar with something like JAX or PyTorch, it operates at a much lower level. So it operates at the level of effectively compilers. So you write your high-level code, it runs through a bunch of either parsing and optimization, and then it does AD on this level. So it targets something called LLVM, or low-level virtual machines. And because of this, it's able to effectively optimize before you do AD. And there's a paper led by Billy that shows that you get asymptotically faster gradients using this, just because you're able to do a bunch of compiler tricks. As well, it is more flexible than I think any AD system I'm aware of. It can handle dynamic control flow, dynamic compute graphs while compiling with no effective performance hits. So you're able to do things that you're not effectively able to do, or at least able to do easily in a performant manner with something like JAX. Because of this, Dominic Chang, a Harvard grad student who I supervise, he was able to write the first auto-differentiable general relativistic ray tracer. So this is a ray tracing tool. We're actually able to take a gradient through the process of tracing light from the black hole to our eye. This is a big boon when it comes to wanting to do anything gradient-based, whether it's Bayesian inference or machine learning. On top of that, there was an algorithmic improvement that enabled this type of performance boost. And that was by moving beyond this kind of survey imaging. So as you recall, you have in RML imaging, you have a 2-component thing. There's a data fit term, so this coded in blue here, and this regularizer term. And what would be really nice is that instead of having to survey over all of these regularizers, is to effectively just optimize and find what the best regularizer is. If you do the really naive thing and just turn these lambdas into additional parameters that you have to optimize over, you effectively just turn off the regularization. The minimum will always just drive lambda to 0, which turns off regularization, which is not what you want to do. And in fact, what you intuitively want to do is effectively balance data fidelity with model complexity. And so what we want to do is effectively find the simplest possible model that can explain the data. And simple here is really encoded by these regularizers. As we increase the regularization, you can kind of think of that we're minimizing the space or the volume of potential images we want to look at. If I have a very, very smooth image, I'm effectively eliminating an entire class of point source type models. And so the really easy way to do this is to effectively reinterpret RML as a Bayesian model. And what this effectively does is we replace this cost function with a posterior, this data term with a likelihood. We also throw out these alpha i's. They're there for historic reasons, but they shouldn't be. as well as an image prior. And then because we're going to include these lambdas as hyperparameters, priors have to be normalized. You have to be able to integrate to unity. As we change these lambdas, we're effectively changing the volume. So in a Bayesian sense, you get an additional term that pops out that's effectively the log of the prior volume. And then what Bayes tends to do is it wants to balance this. It wants to find the smallest volume of model space that can explain the data well. And so it tries to do this balance. So this in volume term is exactly what does this balance modulo priors on your hyperparameters. And so because of this, you can include these lambdas immediately as parameters in your model, and you're effectively adding a handful of additional parameters. So if you stick it into something like a variational inference method or something along those lines, it doesn't impact scaling too much. And so you can effectively, as imaging, immediately do your parameter survey. And this was the big thing that allowed us to effectively automate this. So instead of having to do these parameter surveys, we can just stick in the data, marginalize over all these potential hyperparameters, producing a posterior of images. And so, for instance, here's an example with this pipeline for M87 in 2017, 2018, and as well the AGN 3C279. These are run with identical scripts, no hand tuning, no nothing, and we're able to handle a very different set of image structures. As well, this automation improves science because we're able to effectively search over all these potential hyperparameters. We're able to effectively and more reliably do super resolution. This is an example of the Blazar 3C84. This is the standard image you would get from a clean type method. This is what Comrade gives. And what you can see here is that we have these thin rails. This is actually limb brightening from the jet. If you look at the posterior uncertainty, it's very, very confident that this type of ridge structure is here. And then you see this like ploof and kind of interacting with the interstellar medium and hints of a counterjet here. What's really exciting is you may argue, well, do you trust this super resolution? You know, Clean's got decades of experience, and a lot of clean people will not really believe super resolution. Well, what you can do is you can look at Radio Astron, which is the first ground hybrid or ground space hybrid telescope. And what you can see is that for this one, using clean with a much, much higher resolution telescope, you also see these types of ridges here. So Comrade is at least able to lock on to improve super resolution and in a way that we think is actually reliably extracting data. Now, with that being said, this is a machine learning talk. I do some machine learning. So one of the big things that we kind of have been struggling with, or what we've traditionally done, is we've wanted to take a very agnostic approach to our image structure. So we're in a regime where we don't really believe what we want, believe that we know what we're going to look at. So a lot of the time, our classical priors on our images do not incorporate a lot of physics. They typically enforce loose properties, smoothness, maybe a power spectrum structure. And you know, the benefit of this is the volume of potential images we can explain is really large. The downside is you're throwing out a lot of physics. Specifically, you're throwing out that we really expect this image to look like a ring with some fluff around it. And it'd be really nice to enforce this. One of the ways you can enforce this is by effectively training on the space of simulations of images. This is something you can do with autoencoders. I'm working with a group at Oxford on doing this with effectively denoising diffusion models or conditional denoising diffusion models. Katie's group at Caltech has done a lot of work on these types of diffusion models as well. The other thing, though, is that you can kind of combine your imaging experience with ray tracing. Specifically, I want to shout out Dominic Chang here, who's leading this, is you can start with a really simplified model of what you expect the mean structure of the accretion flow to look like. So specifically, maybe you can imagine, you think of your accretion flow as being two cones of emission. So there's a cone of emission pointed down, a cone of emission pointed up. Turns out that this does a really good job describing almost all the time averaged simulations of black holes we look at. It's shocking how simple of a model explains a lot of the image features. However, there's this turbulent stuff on top of it. So you can add some sort of turbulent power spectrum or effectively image in the bulk of space-time itself. And so you can do this a few different ways. We're using a Gaussian process because I understand the properties of a Gaussian process. You can also do it with neural networks or do something like a neural radiance field. Putting those together, you get an image that looks like this. So you'll start with your simplified model, add a description, and the whole fun thing is because of Dominic's work, we can AD through the whole thing, and we can start doing posterior exploration of this while folding in a heck of a lot more physics than what was done before. Potentially improving a whole bunch of things and also getting the ability to directly assess quantities of interest like spin, black hole inclination, and emission properties of the bulk. However, I am part of a few projects and there's some pretty important stuff that's happening in the future. So the big thing is that the current EHT has 11 sites. We've recorded all this data. However, led by Shep Doleman we're expecting to expand to the next generation EHT where we're going to add 5 to 10 new sites. And instead of observing at 1 frequency, we're going to observe at 3 frequencies. And so as a result, our coverage is going to go from something that's all right to something that's really, really good. And we're going to buy higher resolution because we're going to move up in frequency. And we're also going to get a lot more short scale information. And so as a result, what we're going to have is we're going to move from making a fuzzy image of a ring to a fuzzy image with a ring, but with a jet. And what we're going to be able to see the extended emission and jet structure of M87 and be able to actually connect this jet to the horizon. This is an actual reconstruction with a hypothetical NGHT using Comrade. This is the ground truth, and this is the reconstruction. On top of that, because we're getting a lot better coverage, we're also going to be able to effectively make movies, but make movies in a pretty agnostic way by just at a single snapshot of data, make an image and stitch them together. So this is an example of a flare around Sagittarius A star, where you have this bright region, and then there's some GRMHD or fluid flow behind it, and you can see that we're able to recover this bright spot and even the secondary emission here, and this is done quite quickly. However, I will never forget this, because when we first produced our image of a black hole, I remember the first question I heard at the NSF was, why is it so blurry? Did you try to improve it with Photoshop? And we all laughed, because ha ha ha, it's hilarious. We're not going to use Photoshop to improve that. But it stuck with me, and one of the things that we've also been leading, or Michael Johnson here has been leading, is effectively doing that, enhancing it. And the way we do it is with something called a Black Hole Explorer. And the way this works is we're going to put effectively a telescope in space. Because you put a telescope in space, you're going to increase the baseline length by about a factor of 3, and the resolution compared to the 2017 array by a factor of 5. And so what this means is that we're going to move from a fuzzy ring to finally a ring that has finally potentially being able to measure this thin ring that's predicted from general relativity. It's also going to potentially allow us to take these types of fuzzy ring images of black holes, for instance, 2 sources, probably dozens. It's got a whole bunch of interesting engineering. If you're interested in participating, you should get in contact with Michael Johnson. And so what would a typical night of observation look like? Well, the blue lines show the space telescope, the red the ground. And what you can see is by adding these space baselines, we're getting a very, very big increase in coverage at a very long baseline. And so what this means is that by filling in this long baseline, we're going to be able to turn this fuzzy image from the EHT into something that looks like this. That was, again, produced by Comrade, where it looks better on my screen because this is kind of blurry. But either way, you can kind of see, you can start to see some, and I went too far. You can start to see some aspects of the photon ring here. Okay, not going to use this anymore. And but if you start to time average, now all of a sudden you can really start to see the thing. You can really start to see this n=1 photon ring, or this first photon ring, quite clearly. And so what this means is we're going to move from very, very blurry images to crisp images of black holes. And this, again, will let us to start to understand more important things around these black holes, like the nature of space-time. However, to really enable this, you're going to need the next generation of software. And the reason for this is that you can imagine for 2017, we have effectively something like 10 to 50 parameters. We have a 30-minute runtime. For NGHT, we're going to have to increase the number of parameters by 100x because the field of view we're sensitive to is increasing while we're keeping the resolution the same, and about 10x the data volume. We're also going to observe this at multi-frequency. So just a shout out to Randy Chavez, who's a grad student at the BHI, CFA BHI that I help supervise, who's helping develop multi-frequency imaging within Comrade. However, we're also not going to observe once like the EHT. We're going to observe 30 to 40 times a year. So we're going to go from 300 times the number of parameters to 9,000 times the parameters and 900 times the volume. This is being led by a student that I work with, Rohan Dahale, who's building in some of these dynamical models. And then we're going to move to space. So we're going to increase the resolution. So now all of a sudden we're going to go up to 225,000 times the parameters and 1,100 times the data volume. This means we're going to be taking a very, very long time to image. On top of that, I mentioned calibration. So correlation of the data takes about one to two times the recording rate. That's about as fast as we can get it. Calibration, though, is slow. So to calibrate 1 day of data, with one frequency band, so I mean a 230 gigahertz frequency band, is about a month, weeks to month, depending on the tools. If we increase this to the amount of data we're going to get, it's going to be NGHT and VEX are going to observe 2 to 3 bands, 30 to 50 days a year. So it's going to take about 10 years to analyze 1 year of data. This is a problem. We can't take 10 years to produce an image of a black hole. There's a whole bunch of reasons. NASA will get mad at us is a big one. Don't want NASA to get mad at you. And so what we really want to do, and one of the things we're helping lead with Lindy Blackburn, myself, and Don Pesci and India Natarajan is a solution that effectively, instead of doing Comrade just for image reconstruction, we do a joint calibration and imaging pipeline into one Julia-centric thing. And the way we're going to try to do this is by building a multidisciplinary approach. There's a few proposals going in right now that combines Enzyme, Julia, AstroAI, EHD Julia, Comrade, VEX, and a bunch of statisticians who work at UBC to try to build a multidisciplinary black hole pipeline that will try to get us down into days. So in summary, through I think my big thing is that through computational and algorithmic improvements, we can drastically improve the EHT imaging, turning it into an HPC endeavor, into something that I encourage you to try on your laptop. However, to make this work to the next generation, we need new software to enable this. And this new software joining in right now is potentially really exciting because you're going to be able to make the first movies of black holes, unveil how jets work at these wavelengths and how jets interact with horizons, and really kind of start to disentangle accretion from gravity and make measurements of space-time around black holes. All right, thank you.
All right, thanks so much, Paul, for a very inspiring talk. Are there any questions?
Thanks for a great talk. I really am intrigued by this dance that you have to do between being agnostic about what you're looking at and learning about what's out there and saying, well, I know what's out there, I'm going to make an even better image of it, but then running the risk of not discovering any discrepancies. Do you have thoughts about what guides you as to how much physics you're willing to assume and when you're willing to assume it?
Yeah, this is like a really, really interesting question. And I think it's like, it kind of like depends if you're in like a discovery mode or a measurement mode or something, where I think for the original EHT image and for the original paper, we were really in like a discovery mode where we don't want to assume anything and we want to be very, very agnostic. But I do think moving forward, it's probably very beneficial for the EHT to start incorporating at least loosely some of the physics. So ray tracing is, I think, at least something that's pretty reasonable to do, that we expect light to move on geodesics and we expect black holes to look curved. There's certain things that I would be a little uncomfortable, like if we assume that GRMHD simulations or these hydro simulations that we do are exactly right, I would be pretty uncomfortable with that because maybe they're good at certain things, but they do struggle at things. So for instance, the Sagittarius A star results suggested that the simulations are about a factor of 2 or 3 too variable. And this means something is happening with the physics. And if you talk to the hydro people, they'll be like, yeah, we're throwing out a whole bunch of physics. So there's a balance to be played here. And I think it's something that's going to be really interesting in the coming decades to kind of play out, but I don't have a good answer.
Oh, we have a question online too.
Okay, let's do one and then.
Online question? Sure. So
Yes.
you can unmute yourself.
Oh.
Yes, can you hear me?
Not really, let's see.
Maybe.
Okay,
I'm full.
but
Well,
can you read it or?
yeah, so.
Okay.
If you.
Can you hear me? Can you hear me okay?
Okay, let's continue here then, because it's very quiet, I apologize.
I think it's coming out of the owl, but it's super
Yeah, it's
quiet.
very.
This is super cool. Thanks for this really interesting presentation. And I'm coming from a very different scale. So I come from ISM dynamics and star formation observations. And I must say, I admire people who use clean and all that stuff, because to me, this is black magic. And as you pointed out, oh, this is a signal, this is just noise. To me, this is hard to follow. So I was wondering whether you're, or how far you have talked with these communities, right? I mean, there must be a huge application base in interferometry at large.
Yeah.
And so that is the first part of the question. The second one, slightly related, is what about polarimetry? You have mentioned it in passing at the beginning, but then never since. But you can just incorporate it into your scheme. It's just another feature space, right?
Yeah. Okay. So for the first thing, yeah, they're incorporating into more of interferometry. Yeah, there has been a lot of discussion to incorporate a lot of these techniques into broader interferometry for all the reasons you said. A lot of them utilize clean. And clean is really good at some things, like when you have massive amounts of data, like something like NGHT, or not NGHT, NGVLA will produce. No, I think we're a little far away from scaling to those types, but yeah, I think there's a lot of work to expand these to other domains of interferometry. So we're even talking with Haystack of actually combining this with geodesy, because the Earth reference frame is done effectively doing the LBI, and by using this type of algorithm, we can more efficiently solve for these delays and get a better idea of what the Earth reference frame is. And then things like optical interferometry, they do all the same stuff. We can do optical interferometry too.
I mean, maybe even simpler. I mean, you have the SMA people here in-house, right?
Yes.
In Europe, we have NOIMA, we have ALMA,
Yeah.
which is, you know, the US has a share in it, Japanese have a share in it. There's a huge application base.
Yeah.
Improved interferometric data analysis.
So the part of the this is to actually build tools, generic tools for broad interferometry, with the idea to target things like NOAIM and ALMA. So we can do these types of things. There's some algorithmic scaling that we have to do, but that is the target. And I think in a couple of years we'll probably produce some of these pipelines so that people don't rely on clean, or at least we'll give you some sense of uncertainty.
So if you speak with my friends, it's too early to get in touch with you. Is this the takeaway message?
Depends. I would have to see. In terms of the polarization, yes. The second part of your question, this is how we do it. We incorporate all the polarization effects, instrumental corruption effects into the forward model. So this means solving for things like gain ratios or leakages or other Jones effects. And by doing this in the forward model, we typically perform a lot better than these traditional iterative methods, and we're able to handle a lot better things. Because you asked for polarimetry, and I actually spend most of my time doing polarimetry. One of the fun things we can do is the EHT is a mixed polarization interferometer. So most of our array measures light and circular, left and right circular, almost linear. We traditionally required pole convert, which is basically Alma telling us they think they know what their instrumental effects are and us taking them off. This takes years for them to get right. Some of this algorithmic work we've done, we can effectively do this pole convert automatically within days of the data being correlated. So this is part of the future.
So this is from online. This is from Panayotis Sanavaras from NASA Goddard in Physical Review. Says, thanks for discussing so well all the issues with uncertainties. I think I know the answer, but it's important. Given that the publicized images incorporate the assumptions made and selection of best results, one cannot use these images to derive information, say, on different spacetimes or distinguishing GR versus modified gravity or detecting other features.
Yeah, I would say currently with EHT, us doing the on-GR tests is out of touch. If we knew what the accretion was doing precisely, I think we could get at it. We don't know what's happening with the accretion flow at all. So, and when we try to do things like measure spin of the black hole with the current array, we have no constraints. I would like, if you take this kind of forward modeling approach that Dominic leads, we effectively get flat posteriors in spin.
I have a follow-up to that and the other question. So if you're saying we can rely on that black holes look like curve, is that how flexible is that? Because if you want to be able to, even if you don't have resolution right now, even if you assume curve, we know that higher order corrections to general relativity will only change very small scales. We know that curve is approximately enough. So is this like good enough for a perturbative approach that maybe you assume that for a start and then you let it differ a bit?
Yeah. So the Kerr stuff is interesting. Yeah, if you talk to big chunks of the quantum gravity community, you talk to them where they would expect to see deviation. They're like a Planck length above the horizon.
Exactly.
We'll never get there. It's just like not.
Well, there is one cubic gravity. You can expect larger corrections,
Sure.
but still it's going to be similar to.
Sure. It's different if you expect a correction to happen at infrared, right? So if you have an infrared correction to general relativity, like for instance, let's say we discover lambda-CDM is wrong and there's large infrared corrections, then maybe you would expect to see some deviation to a horizon. I have yet to see a theory that's believable in that sense. So I think we can definitely put constraints on things like quadrupolar deviation to the Kerr metric with EHT. You'd have to talk to the quantum gravity community to see how interesting they are to the types of deviations that we could constrain. But we do have metrics that do expansions around Kerr that we can start to constrain deviations. It's just not from what I would say is a robust theory at this point.
But do you expect with Vex we'll be able to?
I'm going to be happy with Vex if we measure spin.
One more thing was about team. I don't remember the name, but did you try Liam Connor's improved or different? It's similar to Twin but better, if I understand correctly.
So from what I understand with Liam Connors is he has effectively a massive survey of galaxies and low frequency stuff that he trains a neural network on and kind of can do an iterative type clean mapping. Is this the?
Thanks.
I don't think we've tried Liam Connor's things. I think we can definitely apply that. I think Liam's work is really interesting because he's in a regime where it's like DSA 2000, where DSA will literally never record the visibility data and they will immediately throw it out. And so they need some like really fast live pipeline. It'd be interesting to see how well Liam's methods work when we have this incredibly sparse array that we play with.
Just mostly a comment, but Alex Upskasa says Beck's observations of the n=1 ring will assume the Kerr nature of the sources to infer their black hole parameters, mass and spin. In principle, future observations of the n=2 proton ring would offer stringent tests of the Kerr hypothesis and GR, the strong field regime.
Alex is one of the leads of NEXT, so.
Okay. Well, thanks, Alex. Any other questions, comments? Discussion? Anyone online? All right, okay, so, let's thank Paul again. Thanks, everyone. Next week, we don't have an AstroAI meeting because it's a holiday, but we will have one